So next up is Nikola Todorovic with hacking smart contracts.
Thank you everyone. Okay, so let's start. So today's topic is exploiting smart contract vulnerabilities, and we want to approach it just from a security side. Like take a look at, let's say, a new system. Forget it's a blockchain. It's something that's what's hyped so much. Let's take a look like from engineering perspective, like what is the system and how it can be exploited. What are the common errors and what exists there. So yeah, let's short introduction about me. So yeah, I'm currently working as a lead blockchain engineer at a company called Origin Trail. We develop like a decentralized knowledge graph, which is like the main thing, but also we develop a Origin Trail parachain, which is one specific type of a blockchain. Also, I'm coach of Serbia national cybersecurity team, which competes on European cybersecurity challenge, and also organize the Serbian cybersecurity challenge, which is some kind of national CTF. So yeah, anyone younger than 25 years old, get in touch. We can speak about including in all this fun stuff. Also, maybe know me from other cool projects that we have here, which are more local for Serbia. And yeah, you can contact me via Twitter or ask me after the presentation. So let's get into the content. First, let's put some basics. Like what I was also surprised, like when I started researching this topic, like this concept, like idea of smart contracts, it appeared back in the 1994, like by American scientists from Hungary, which defines smart contract as a computerized transaction protocol that executes the terms of a contract. But at that time, it was not so feasible to implement something like that to be secure and developed. And at the moment when the blockchain appears, which let's say the definition is a distributed ledger with a growing list of records that are securely linked, and the cryptography hashes, the whole cryptography make it secure and make it feasible to have the smart contracts today as we have them. So the appearance of blockchain give us the smart contracts which don't have like a pure definition today, but we can define them as some programs stored on a blockchain, and they will run when there's some conditions fulfilled. And some, let's say, characteristic which we can take in consideration regarding smart contracts is they have automatic execution. Once some conditions are fulfilled, they will change from one state to another. They should be unstoppable. Like you should not be able to, if something is agreed between two parts, it's defined as smart contract. If some conditions are fulfilled, no one should be able to stop it. Also, it should be mutable. It should be once deployed, that's what will be. No one can change it later. And probably the most important one, they should be secure. And it's the most problematic part here, the hardest to reach. So the context where everything happens and where smart contracts started is the Ethereum blockchain. So it's the second largest one and the popular one after the Bitcoin. It has the currency called Ether. It has 44 million smart contracts right now deployed. And let's say execution environment, it's called Ethereum virtual machine, which is quasi-Turing complete state machine. Why quasi? It's all like a regular state machine that you have, but you have one limit. There is, for each thing that you want to execute, you need to pay for it. There is some kind of a gas defined. You need to pay tokens for execution, and infinite loops are impossible. You will run out of the gas and the program will stop. You will see later why is this important. Most common programming language is Solidity and Viper, and we'll see most of the errors that can be exploited and that are the most easiest ones to exploit are the ones that appear on the highest level when we program in Solidity, for example. So yeah, the most basic example, just to understand what's the program that we're looking into. Definition of the programming compiler at the top, then we say contract calls simple storage. Each contract has some that's stored inside of the chain, some values. This will have only one unsigned integer, stores data. It will have one setter and the getter. Syntax is something like a JS, simple to understand, a bit couple additions that make it compatible with the Ethereum blockchain. For example, you also have some additional things like here in the getter you have like definition that it's view, so if it modifies anyway a state, this will fail at the compilation level. So there are a couple of things that's already built in, but there's also a lot of things that are missing here that will make this more secure. So how it starts? We can say like a regular contract is someone agrees to do something. It's one, two parts or multiple of them, does not matter. They hire a developer, he develops some smart contract, compiles, we get some bytecode, which is then deployed on the network. It's stored inside of the blocks, and when we want to execute something, we just call a function to that smart contract. Calling the function is like sending a transaction. So we can send tokens from one to another, but you can also pay for some execution. So each step you call a function, you just move from one state to another one. It's all about that. So state machine, changing states, and our main point is like with every system, we should get it into unexpected state. We should make it do something that it was not designed for. So let's start with what are some vulnerabilities here. Most smart contracts deal with financial assets, and it's like you put a target on their forehead. Like this is something that you should hack if you want to get some money. So they should be super safely developed. But the thing is, like, the paradox is that they're super fastly developed, and there are a bunch of funny mistakes, funny errors, which we'll probably see in the next talk a bit more. Here I'll be focused more on examples, how it looks like. So yeah, money is insane from my point of view. So like there is now stored 300 billion in smart contracts, and each year increases the number of how much is stolen. So 1.3 in 2021, 3.8 in 2022. Even if the hype slows down, the money gets more and more stolen there. So just to get them into some perspective, where they can occur, the vulnerabilities can be on the highest level, is the solidity, the easiest one to exploit. Then there is the EVM, exploit some parts of the state machine, how to use some specific theirs, and there is the lowest level on the blockchains where the validators, miners can tamper with the data and make some things unexpectedly happen, but this is like the hardest one to reach. So the easiest one to exploit and the most common things happen are on the highest programming level. So let's start with probably most of your favorite list, OAuth's top list. And yeah, from last year, there is also one for smart contract vulnerabilities. Here's a list of them. We'll go them through practical examples, but some of them are, let's say, easier to understand. Some are like generic, like logic errors. Okay, it happens everywhere. We cannot just with simple, we can with simple examples show it, but it won't give you more understanding of the issues. Like then denial of service is something that can be triggered by also access control vulns or by logic errors or gas limit issues. So you will see how we can combine some of them, how they overlap a bit. So we can start with the one that's most common and probably the deadliest one. It's called reentrancy. It's a simple concept. If you have been doing some concurrent programming, you should be familiar with the idea, but we can define a reentrancy attack or just general reentrancy when a function is externally invoked during its execution, allowing it to be multiple times run in a single transaction. So here is some simple contract. What we should focus here, it has one function to deposit. We can give some money to the contract, and there is another one to withdraw, get back the money. So the first here just increases the balance. Balance is a simple hash map. So it will say for this address, we will store that amount of money. So when we receive some tokens, we increase the balance. We want those back. What we'll do? So first, let's do a check. Let's see if this message sender has that amount of tokens stored in this contract. If he has, we'll proceed. If not, this will revert. Then let's give it back to him. Let's transfer those tokens. So to the message sender, transfer the value that he requested, and then let's update the balance. Let's change the value in the hash map. And on the first thought, this looks fine. Okay, I will do step by step. Everything I have a check should be fine. This transaction, it will run only one. There cannot be interference or something. But there is one interesting concept that they introduced here. It's called fallback functions. So this is thing that's introduced specially for the Ethereum EVM, and it's like a special function that's executed in two cases. When there is something called by smart contract, when there is a function that does not exist, it's called. So if we have like a call my contract.pawn, I don't have a pawn function, then the fallback will be executed. Or when someone is sending tokens to me, so someone is sending tokens to my contract, if I define some logic, for example, receive, which will do some internal changes of the state, we'll have execute the fallback all the receive function. In this example, like what the attacker can do. So someone can deploy, so the first vulnerable contract is the A. And if I deploy contract B, I can start the attack by, first I will deploy some tokens. There will be a hash map, there will be something from a address of contract B where there will be 1 Ether deployed by me. And I will initialize the attack by just calling from another contract the withdraw function. And I would want back my money, so it should withdraw all the Ethers back to me. And okay, first step, I'll check the balance, it's fine. Next step, send the Ether. Cool, getting back 1 Ether to the contract B. Here we go, fallback function, and inside of it, we get back. We enter again the withdraw function. Where are we at? We are at the start again. We check the balance, it's still 1 Ether. We go next step, we send the Ether. Okay, here it is, 2 Ethers in the contract B. Fallback again, enter withdraw, stall 1 more token, and just drain out the account. You can define some conditions when will you stop draining out to avoid some mechanism that exists. And this is not always like this plain simple, but you just do it. Once you finish it, you just stop the execution. Balance will be set to the 0, but this contract A won't have any more 8 Ether, it will have far less. So in the practice, this is like not like direct like this. There are like indirect calls, there are hidden things, but like this is the logic of the attack, and this is the most common one. So next one, I mean, this sounds silly, but integer overflow and underflow. I mean, it's quite common across all the languages, but here it has a higher impact. Like when you do with the numbers here, you need to be absolutely careful. Those numbers usually mean some amount of money. And the most basic example is here. 8-byte integer represents number of loans. If I take one more, I will increase it to 256, which in computer science means it's now 0. So I don't have any loans. I'm now free man. And this, it takes like 0.8 version of Solidity to make it revert when there is any overflow or underflow. So it's like from 2013 until 2018. So that amount of years that's required to implement those things, and I would say it took them too much. I don't get the context why so, but it should be fixed much earlier. And yeah, you can use this, delete number of loans. You can mint an excessive amount of tokens, which means you just print some money for you. It's just simple as that. Or something less complicated is to bypass some time lockers. So you put some tokens, they will be locked for some time. You can increase that lock time to get some advances. You just push that time locker until you get the overflow. So, and then if you mint an excessive amount of tokens, that leads to hyperinflation of token, which means like too much tokens in circulation, the price goes down, no one wants it, everyone sells it, and the whole project is failed. So this is one example for practice. It looks fine, it's quite simple, but let's say we want to do a batch transfer. So I want to save some gas for transactions. I will send to multiple accounts with one call. I will say, here is an array of receivers, and here is the value. So I can send to all the people in the first row 1 Ether. I will provide their addresses, so I will check how many of them is. I will define what amount of tokens I need to send. So if there is 5 people, 5 times 1 Ether, I should have 5 Ether here in the contract. So let's see the first check. Is the count higher than 0? Yeah, it is. It's 5. Is less than 20. Security measure, why not? It's less than 20. Is the value higher than 0? Yeah, I want everyone to send 1 token. Is the balance, my balance, higher than the amount that I calculated? So it's 1 times 5, it's 5. I have 7 in the contract, it's fine. We'll do the sending here. But what happens here? Where is the issue? So this calculation here can lead to overflow. We can provide some numbers that will overflow. So value that's valid, for example, let's see, let's make it directly to the exploiting part. So here we'll say 2 receivers. To each I want to send the half of the maximum value for unit unsigned integer plus 1. So I will be sending here 2 times half of the maximum value times 2, which will overflow, which will take to the 0, to the 1 at the end. So the value will be higher than 0, the amount will be 1 token, which I have, but at the end I will be actually minting almost the maximal half of the maximal supply to those 2 addresses that I want. So quite simple and huge impact. Now, denial of service. So it's not the same denial of service that you're used to in computer science. So you get something out of work for some time. Here's the thing that you're able to take it offline, I mean, out of the control forever if you get some denial of service. And it can be as a result of other vulnerabilities. So if you abuse access control, you can stop some contract, use gas limit vulnerabilities, or some logic errors. So let's get directly. So the guy said, I accidentally killed it. What happened? This is one well-known hack. There is a library that's used by a bunch of deployed contracts. And that library has an open initialize function. And there is also a function to kill, to stop the smart contract. And the guy called, okay, I will init, I will set myself as the owner, I will delete it, and now I have locked the value, which was at that time like $300 million. All those, and it was like you deployed 1 wallet with that library, your tokens are locked. And he accidentally did it. I mean, we can discuss that if it's accidentally 2 calls that destroyed the important contract, but it was fun. I mean, it's still fun with those things here. Another one, gas limit issue. So, as I said, it's a quasi-Turing machine. So you cannot do an infinite for loop, even less. So there is a limit of execution that you have to use, and that should fit into a block, 1 block of blockchain. So here, this looks perfectly fine. We have some hash map of the addresses. We want to refund, give back the tokens. We just iterate over all the users and we just send them tokens back. But what happens here, if I try to create too much users, I will hit the limit. So if I create like with a really, really small amount of tokens, new users, I put as much as them in this refund mapping. Once when someone tries to execute refund DAL, it will get stuck. It will hit the gas limit and it will block all the tokens of all other users in that contract. So they're doomed. They won't get back those tokens from this contract. This is with US with block gas limit, and then with this is part of the unchecked call and also logic error, let's say. This is some simple game that demonstrates one issue. So it's called King of Ether. Idea is someone can be the king for some time. You just give as much tokens as possible. So you say, I will claim the throne. I will give 2 tokens, and I will be set as a king until someone else came and said, okay, I will give 3 tokens. And they will go, okay, I will send back tokens to the current king. I will give back those 2 tokens, and I will set you as the king. And what happens here, that's, let's say, unexpected, is if the caller is a smart contract. If smart contract says, I want to be the king, here is tokens. This will work fine. This will set him for the king. Will set the new balance. And if someone wants to overthrow the smart contract king, then there will be some issues. So the king call and send balance function here if it's sent to another smart contract, not to regular account, but to smart contract, and there is no that fallback receive function, this will fail. And this will never pass this part. Our smart contract will stop fully this coin. It will be an eternal king of it. And okay, let's fix it. Let's check if the caller is a contract. If it is, we won't allow it. Fine. How we can do that? Well, we need to go a bit lower level. We need to do a bit of assembly here. We'll call this operation code get me code size of the account. Let me see who the caller is. And if it's a regular user, he won't have any bytes associated with it. If it's a smart contract, it will be the byte code. It will be the code of the smart contract, and you will know it, okay. If the size is greater than 0, then it's definitely a smart contract. But it's not that easy. It's funny because you can exploit this by another simple mechanism. The way when you create a contract, you deploy it to the network, and you say, okay, there are steps to execute. You need to store some value on the blockchain, you need to execute the constructor, you need to set some values, and so on. And the steps go like that first, the constructor is executed, and after that, the size on the count is set. So we are calling here in the constructor we just will say here what we want to do. We want to claim the throne inside of a constructor. It will be executed. It will send the claim throne function. And after that, all that execution is finished. The EVM will set this code size of the account to the size of the contract. So we avoided this contract check. We set up ourselves, and we are now the kings again. Okay, let's move forward. So this gentleman here called the caller, he has some contract, and he can implement that contract in different ways. He can use the call, which will execute function from another contract. So his call is just executing inside of contract B and setting some values inside of contract B. But there is, again, delegate call, which is get the code from another contract and execute inside of my context. So change the things inside of my contract using some other code. And this is practical. You want to develop some libraries. You want to use them, and you want to use them in 10 contracts. You want to deploy 10 libraries for each contract, and then connect. You will use one library, and you will execute in a different context. So delegate call will preserve the context. It will use the storage of the contract caller. It will use the message sender, everything. It will just use the code of the different libraries. So what's here happening? So here it is, concrete example. This is some library. It has some storage. It has some number here. And this library is doing some useful stuff for us, but it also set this internal number to some value. So it is able, using that library, to change its state. And then we have simple contract. It will say here, okay, it will initialize, set up the library, connect everything. It will have function which is doing something. And this function accepts the number, goes here and says, okay, delegate this call to library, take the code, and do something with that, call the do something function, that will do some calculation, will set some values there. And what's the problem here is that when we are calling this do something, it's executed in this context. So this is the storage layout that we have. First thing in storage is library address. Second thing in storage is the owner. Third thing is the some number. Library thinks that the first thing in the storage is some number. It will try to modify it. And if we call it like this, do something, convert to integer my address. So I will say to the go here. So it will get my address here as an integer. It will delegate call to the library. Library will set at the first place my address. And what is here actually, it's actually the library address. So I have overwritten the library address inside of the vulnerable smart contract. With this, I can now call hack me do something, which is I set up myself as the library. So this exploit contract is library, and it will call set the owner to the message sender. So I will set up myself as the owner of this contract. I'll take over full of it, and I can do whatever I want. So this is all about those simple examples of how to exploit them. Then there are some other mentions. So unchecked external calls, this also can happen, lead to logic errors. If you use some specific calls, the sending can fail. And if you don't check the results of the sending of the tokens, you can proceed with execution not knowing that the tokens are not sent. You will get in unexpected state, which will lead to more issues. Then front-running attacks. Okay, that's not something that you can like exploit right now. It's more like a bot thing. So there is a full network of bots which are monitoring what's happening. If they see that someone is drawing out money from tokens, they see some malicious activity, they will try to get in front of you, to steal the tokens before you. How is that possible? Well, that gas concept that I said, you're paying something for execution. Well, it's not, you need to say how much do you want to pay for it. Like there is amount of how it needs to take, but also how much of priority is it. So if you pay more than me, even if you came 5 seconds after me, your transaction will have the priority. It will get into block before mine, and you will, let's say, steal something before me. Then, okay, insecure randomness. Randomness is generally a problem here. All the validators in the network need to agree on what is a valid block. They need to validate it, and they not have like the proper source of randomness. And smart contracts usually use block timestamp or block number as a seed for the randomness, and with control of small portion of validators, you are able to manipulate randomness to predict and then take over predict what will happen in some contracts and get them in an unexpected state or win some lottery contracts, whatever. Then timestamp dependence. At the start of the Ethereum, you were like the miner who is creating the block, he was able to change the time 15 minutes up or in future or in past, how he likes it. And if he wants to alter some things, how they happen, if the contract is working with the time block .timestamp, he can do some malicious things. Now it's far less, it's I think 5 seconds he can alter it, but like never trust the timestamp, just go with the block numbers. And yeah, let's give some recommendations, just not to have the hacking, let's give also the securing part. So the first thing regarding the reentrancy, what we have done, we checked if everything is fine, we send the tokens, and then we updated the storage. Well, let's change the order. If we do the check and then update the local storage, after that we can send. If the send fails or do something unexpected, if it tries to enter again, it will see that the storage is already set to 0 and it cannot use any tokens. So check effects is the pattern that's called, and it's something that everyone should do when they're implementing any functions that could be re-entered. Pull or push. Don't try to push tokens to anyone. You don't know what's on the other side. Is it a user account, is it a smart contract, it's something malicious or not? Let the user get here and pull the tokens for them. Implement circuit breakers, I mean, as, let's say, call it panic mode. If you see something is unexpected, let's say you have a trigger to stop all the functions that are important for the system, let them only like withdraw, let people take out the money out of the contract and don't do anything else. Formal verification, of course, as for any program it's required. Use well-known libraries, like the ones from DOP and Zeppelin, which is well-known in the industry. If it's possible, limit the maximum number of tokens that you can accept and handle. So just recommendation. Also, don't forget, all data is public on the blockchain. So you cannot hide things that easily there. You need to be aware of that. And yeah, there are functions called kill and self-destruct. We can destroy contracts. They can create a bunch of issues. Usually it's a good thing to not have them. Like you need to have good reasons to have them there. There are some tools. They can make your job easier, but not that easier. It's far from ready for some serious, like it cannot be compared with other industries yet. And there is a lot of space for anyone to jump in, create tools, start doing this security audits and different stuff. And let's see, the final one, useful links. Yeah, we'll have the shared presentation. You can go and play, look at this. So there's some nice tutorials here for some hacks, some recommendation, and yeah, we all like to get hands dirty as soon as possible, jump into those examples and start playing around, hacking some contracts. Thank you for listening, and my QR code is not working. Not sure why. Let's see. Here it is. So yeah, presentation. Okay, here is QR code. Here is the presentation. You can take it. I'm open for any questions.
I think there's one question, right?
Okay, thanks. As one of the recommendations, you mentioned that smart contracts could be formally verified. So, do we have any like real-world examples of formally verified smart contracts?
Honestly, no. I don't know. I know there are some tools that doing that, some research mostly. I'm not sure about the state of formal verification of smart contracts right now. So,
Anyone else?
cool. Thank you.